In this video, we're going to take a look at relative motion, which is a great example of vector addition. Common examples include airplanes in the wind and swimmers or boats passing through a current.
Okay, let's take a look at relative motion in one dimension. So I'm going to draw a bus, and on that bus I'm going to put a person, and let's say that that person is walking towards the front of the bus at 2 meters per second. And we'll say that the bus itself is moving forwards at 5 meters per second. And we can imagine another observer here on the ground watching this whole process. Now, whenever I give a speed or velocity, I should say relative to what? So this 2 meters per second is not relative to this guy on the ground. It's relative to the bus itself. And so I really need to specify, when I say 2 meters per second, I need to say relative to the bus. Now, this 5 meters per second, I should also say relative to the ground. But we usually don't say relative to the ground, because relative to the ground is kind of the default. And so if we don't say anything, we imply that that 5 meters per second is relative to the ground. I think most of you could see right away that if we imagine this bus going invisible and we just saw this guy's head moving across, then we would see his head moving across to the right at 7 meters per second. So this observer on the ground would simply see this guy's body moving across to the right at 7 meters per second. And that is the default value. That's relative to the ground. That's the default reference frame. This was really a vector problem. What we did is we took that 2 meters per second as a vector, 2 meters per second, and we joined it head to tail to the 5 meters per second of the bus. And from that, we got a velocity that's relative to the ground, or we'd call that a resultant velocity. Or we could say the velocity relative to the ground. But the key thing I want you to see here is that it's really a vector addition problem. And then when we treat it as a vector addition problem, then we can work up towards two-dimensional problems. Let's look at the same problem, but this time let's have the guy walk to the back of the bus. So this time, there's his nose. There's his nose. This time there's his mouth and his eye. He's walking to the back of the bus at 2 meters per second. And we've still got the bus moving forward at 5 meters per second. And once again, we can use this vector addition. So if the bus suddenly went invisible, the observer on the ground would see this man doing a moonwalk. He would be facing to the left, but he'd be moving backwards at 3 meters per second. And once again, this is really a vector addition problem. We've got the motion relative to the bus to the left at 2 meters per second. And we're adding that as a vector to the motion of the bus itself, the 5 meters per second. And of course, the resultant vector goes from that first tail to that last head, and it would be 3 meters per second to the right. Okay, so let's move the problem here to 2 dimensions. So we're going to have a subway platform, and we've got this guy here, an observer on the subway platform. This guy here, he's going to move across the subway car, but we're going to imagine a subway car with the walls torn off. So we've really just got a moving surface here. And that moving surface is going to move across to the right at a constant speed. Let's give it a speed of, say, 5 meters per second. Our walker, we're going to put him right here, and relative to that moving surface, we're going to make him move at 2 meters per second. Now, of course, to this guy over here, what he's going to see is not simply the motion at 2 meters per second straight across the car, but he'll also see the man moving to the right at 5 meters per second. So what we want to do is do this again as a vector addition problem. So we've got the motion relative to the platform, 2 meters per second down. And then we want to add that as a vector to this 5 meters per second, the motion of that moving surface. And then our resultant has to go from that first tail to that last head. That would be our resultant velocity. And that's what we want to find out. So we'd like to both find out the direction and the magnitude. Well, the magnitude is very easy. The magnitude, we can see we've got a right angle triangle, so we can simply use Pythagorean theorem, 2 squared plus 5 squared. Take the square root of that, and you should get an answer of 5.4 meters per second. And let's try to solve for this angle down here. 2 is the opposite side, 5 is the adjacent side, so that means that theta has to equal the inverse tan of the opposite side, the 2, divided by the adjacent side, the 5. And if we work that out, we get 21.8 degrees. Relative to our guy on the platform, it's going to make a motion kind of like this. This is what he's going to see. Most of the motion is due to the moving car. And then there's some added motion due to him walking across. And of course the subway will move along, so he's still staying right along that dotted line. And so the angle that we've just calculated, that 21.8 degrees, is right here or here. So what we're seeing is that he would go off at this 21.8 degrees from this vector to the right. And he'd be seen moving at a speed a little greater than 5 meters per second. Okay, let's do a little variation on our platform problem. So what we're going to do is slow down the platform to 1 meter per second. And so instead of having the man walk straight across this orange line so that he's moving directly across the moving surface, what we're going to do is have him walk directly across from the view of the platform. In other words, he would step on the moving surface at this dot and then step off at this dot. So he seems to be going in a straight line as seen from the platform. What that means is he's going to have to aim himself more in about this direction. He's still going to have the same walking speed of 2 meters per second, but now he's got to make up for the fact that the platform is going to move forward in the time he walks across. So what we want to do here is to add up those two velocities, his motion relative to the moving surface plus the motion of the surface itself. So we know the man is walking at a speed of 2 meters per second. We don't know what his angle of orientation is. We'd like to find that out. And now we need to add that to the 1 meter per second, which is the motion of the platform. And we know that that's directly to the right. Now when we add up those two vectors, we get a resultant that goes straight across, and that would be the resultant velocity, or the velocity relative to the platform. So we'll call that vector VR. Now to get the length or magnitude of VR, we can simply use Pythagorean theorem. The hypotenuse squared, that is 2 squared, has to be equal to VR squared plus 1 squared. So we're going to get that VR is going to equal the square root of 3, which is about 1.7. So he's going to appear to move at 1.7 meters per second. And note here that it'll be kind of interesting. As seen from the platform, these would be his shoulders, that would be his head. He would be facing or heading this direction, but his movement would be straight across. Now to find out this angle in here, theta, we can say that the sine of theta will be the opposite over the hypotenuse, 1 over 2. And that means that the theta must be equal to the inverse sine of 1 over 2. And that comes out to be 30 degrees. So this angle in here, the angle he's got to aim at, is going to be 30 degrees from going straight across. Here's an excellent little simulation from the physics classroom. And what I want to point out to you here is that the boat river problem is exactly analogous to our moving surface platform problem, because the current of the river is just like a giant moving platform, moving at a certain speed. And the boat speed in still water would be exactly like the man's natural walking speed across the platform. So in the same way that the man would, say, aim himself straight across, but because of the motion of the platform, he would end up over here somewhere. The same thing with the boat. Mathematically, it's identical. All you're going to have to do is add up that vector for the current to the vector for the speed of the boat in still water, the kind of the natural speed of the boat. And you'll get a resultant vector, a resultant velocity, that will be the motion of the boat as regarded from the shore, or as regarded from the ground. And if we adjust the parameters in the simulation a little bit, we can make that boat go straight across the river. But note that it is aiming in this direction. So we would have that natural velocity of the boat at 9 meters per second, and you're adding that to the river speed at 3.4 meters per second to get a resultant that goes straight across. So once again, if you know the moving surface and platform problem, then you know the river and boat problem. Here's a very interesting question from Paul Hewitt. We've got 3 identical boats. They all have the same natural speed in still water, and that would be represented by the pink vectors here, the length of the pink vectors. The blue vectors represent the current, so the current is the same for all the boats, and they're going to travel across a river. And we're asking 3 questions. Which one is going to move with the highest speed? Which one is going to take the least time to cross? And then which one is going to travel the shortest distance to get across the river? So pause the video, try that now, and then come back for the answer. So naturally, what we want to do is work out the resultant vector, see what the resultant vectors look like to answer these questions. So I'm going to add that current vector onto the pink vector. Now I could create a full parallelogram here. I'm going to be a bit lazy and just go from that first tail to the last head in each case. The black vector here, and too lazy once again to use a ruler. But these would be the 3 resultant vectors in each case. So the first question, which one is moving at the highest speed? Well, the one with the highest speed, you're looking for the one that's the largest magnitude resultant vector. And clearly that's going to be the case for C here. This black vector is longer than that black vector or that black vector. So the highest speed is going to be case C. Now, for the least time to cross, I think it becomes very obvious if you think about the platform itself. If you want to walk across a platform, whether that platform is moving or not, the way to get across the platform in the least time is to aim yourself to head directly across. So to get across in the least time, you want to head directly across. And so if we look over here, which one is heading straight across? Well, there's your heading right there. That's the pink vector. That's the one that's heading straight across. So the best answer there, the right answer there, is A. Now another way to look at this problem is to think about which one has the largest component of its resultant directly across. And if we do that, okay, here's our resultant in the first one, and this pink vector would be the component directly across. In the second case, here's your resultant, and the component of that resultant directly across is that black vector itself. And that black vector is shorter than the pink vector. And then down here, the component of the resultant that is directly across would really be that vector here going up to this point. But once again, that component is going to be shorter than the pink vector in A. And now in part C, we're asked for the shortest distance. Well, of course, the one that is going to go the shortest distance is the one who's got a resultant that is directly across. Not who's heading directly across, but whose resultant is directly across. And the one that's got a resultant directly across is, of course, B here. So 3 questions that seem like they might have the same answer on the surface all had different answers. Okay, we have a numerical example for you here. The IB is not going to give you a question like this. So if you're not getting this, don't worry about it. But I think it is an important topic, and I think for many it's a favorite topic, so I did want to do a question like this. And you will do a lot of this in math as well. So what I'd like you to do is read over the question, try the question, and then come back for the answer. The first thing that we need to do is to figure out our resultant vector. Everything's kind of backwards in this one. We're going to go from Calgary up here to Edmonton, and it's going to be due north, and the speed that he's going to have to travel at is going to be 300 kilometers in half an hour. In other words, 600 kilometers per hour. So we already know the resultant vector. The VR is going to be 600 kilometers per hour at due north. So he's got to end up going due north. So we know our resultant, and then the other two vectors in the problem are going to have to add to that. So if we start with our wind vector, it's supposed to be 50 kilometers per hour at 50 degrees. So let me do it in orange. This will be my wind vector. So it's got a 50-degree angle here. That's 50 degrees north of east, and it's got a length as well of 50 kilometers per hour. And then the other vector, which I'll do in red here, that's going to be our heading vector. That's what we're looking for. So I'm going to add this wind vector to a heading vector. And that heading vector would tell us what direction the plane has to face its nose. So in this case here, we want to find out that angle to find out what direction the nose of the plane has to face. And then we're going to have to try to find out the speed here. The length would be representative of the speed. That would be the still air speed, the speed relative to the wind. So this one here is going to be the velocity. So this vector here represents the velocity with respect to the wind. So we might call that the still air velocity, or we might call it the natural velocity of the plane. But that's what we want to find out. So let's do the problem using vector components. Works out very simply that way. So I'm going to denote this wind vector by a W. And I'm going to denote the velocity with respect to the wind. I'm going to denote that as P for the plane vector, meaning that's the natural speed of the plane. Now, here's my VR. So that means VR has to equal the vector sum of the plane vector and the wind vector. So let's write everything we know in there. The resultant vector has got to be straight north, and the speed is 600 kilometers per hour. Is going to be 0, 600, because it's directly north, directly up. The wind vector, that's going to be 50, the length of the vector, times the cos of the angle, and that is the natural polar angle, that 50 degrees. So it's going to be 50 cos 50, and then 50 sine 50. And then I'm simply going to represent the plane vector as px, py. Those would be the Cartesian components of this vector p here, this vector here. Okay, so let's do the math. 50 cos 50 turns out to be 32.1. So this vector is going to be 32.1. 50 sine 50 turns out to be 38.3. This is Cartesian components, so the math is really easy. That means my px and py have to be equal to 0 minus 32.1. So that means that I can isolate this px, py on one side of the equation, and on the other side of the equation I'll get 0, 600 minus 32.1, 38.3. And of course, in Cartesian components, all we do is add or subtract the components. So we're going to get 0 minus 32.1 and 600 minus 38.3 to give us our plane vector in Cartesian components to be negative 32.1 and approximately 570 for py. So to go from Cartesian components back to polar coordinates, I can get the magnitude, or the length, of the vector p using Pythagorean theorem, 32.1 squared plus 570 squared, and that gives me approximately 571 kilometers per hour. So the wind would increase his speed just a little bit, but not much. Now for the angle, it's going to be the inverse tan of the y, which is 570, over the x. The x is really negative 32.1, so we have a negative x component, and when we have that negative x component, what we have to do is add 180 degrees to our answer. And when you plug that in, you should get an angle of 93.2 degrees, and that's the polar angle. So if we express that as a heading, it would be about 3.2 degrees west of north. So our final heading would be 3.2 degrees west of north. So even though the wind was quite strong, it didn't make much of a difference to the speed, just 1 kilometer per hour, and didn't make a lot of difference to the heading, just 3.2 degrees. However, that will be very important to pilots, especially over long flights. So in summary, when we're looking for these resultant velocities, which are velocities usually relative to the ground, what we're doing is we're adding two vectors to get that resultant velocity. So one vector always represents the motion in the moving frame. That would be our walker on the subway train. It would be our walker on the bus. That would be our boat moving through the moving water, or it would be our plane moving through the moving air. Vector you're adding that to would be the motion of the frame. So that would be the motion of the bus itself, or the motion of the subway train, or it'd be the motion of the water itself, or the air itself. And you add those two together, and what you get is this resultant velocity, which was, in all the cases that we looked at, a velocity relative to the ground.
So please take the time to like videos, to make comments, to ask questions, become a subscriber, sign up for notifications, become a member or a Patreon.
And that's all for today, folks. Thank you very much.